Today we're going to look at a rule called L'Hopital's. Sometimes it's spelled L apostrophe hospital. Pronunciation here is going to be L'Hopital's rule. So what we're going to do first is we're going to start with the statement that we have f prime of A over g prime of A, which starting there, we're going to make the assumption that both f prime of A and g prime of A exist, and that g prime of A is not going to be equal to 0. We'll start with that assumption. G prime of A is not equal to 0 here because otherwise we have something undefined. And we could write this out using a limit definition of the derivative, saying that f prime of A is just equal to the limit as x approaches A of f of x minus f of A over x minus A over the limit as x approaches A of g of x minus g of A over x minus A. We remember way back to the beginning of our unit on derivatives, this was one of the two forms of the limit definition of the derivative. And when we have a limit that's separated, or two different limits that are separated by division, as long as neither of the, as long as the one of the denominator is not equal to 0, which we know that that's the case because we already stated that g prime of A wasn't equal to 0, we can turn that into one singular limit. So we can just now call this limit as x approaches A of f of x minus f of A over x minus A over g of x minus g of A all over x minus A. And then another thing we know here is that anytime we have a fraction within a fraction and both the denominators are the same in that complex fraction, we can just eliminate those denominators. So, it's a fraction divided by a fraction, we can multiply by the reciprocal, and then we have an x minus A over an x minus A. Those would cancel out. So we can rewrite this as a limit as x approaches A of just f of x minus f of A over just g of x minus g of A. And from there, there's not really much else we can do except that, well, I know in advance what L'Hopital's rule says. The L'Hopital's rule says that if we have an indeterminate limit of the form 0 over 0, a limit as x approaches A of just f of x over g of x, so without this, it's equal to f prime of A over g prime of A. And so what we're actually going to do here is we're just going to say, suppose f of A is equal to g of A is equal to 0. Well, if they're both equal to 0, f of A and g of A is equal to 0, then that would tell us, if we were looking originally at a limit as x approached A of f of x over g of x, well, that'd be f of A over g of A, which would be an indeterminate limit of the form 0 over 0. So supposing that this is true, we just end up with the limit as x approaches A of f of x over g of x, which we now know to be 0 over 0, is equal to what we began with, which was f prime of A over g prime of A. And we know, since these functions are differentiable, we can assume that f prime and g prime are both going to be continuous functions because we were saying that at the beginning that f and g are differentiable functions. If f prime and g prime are continuous, then that would mean that at A is continuous at that point. And that would tell us then that f prime of A and g prime of A would just then be equal to a limit as x approaches A of f prime of x over a limit as x approaches A of g prime of x, which could then be rewritten into one singular limit. So we can say that the limit as x approaches a of f prime of x over g prime of x is equal to the limit as x approaches a of f of x over g of x if f of a equals 0 and g of a equals 0. Now, we're not going to get into a longer, more developed proof of this because it requires some things we don't really talk about in this class, namely the Cauchy mean value theorem, which at some point I'll probably make a video and put up the Cauchy mean value theorem and an extended proof of L'Hopital's rule. But the cool thing about L'Hopital's rule, besides that it just works here for 0 over 0, it actually also ends up working when f of a and g of a are positive or negative infinity. And so if we have f of x and g of x being differentiable functions on an open interval, and g prime of a not equal to 0, and f of a equal to g of a equal to 0, or f of a and g of a as positive or negative infinity, this rule, L'Hopital's rule, will apply. And we can just take the derivative of the numerator and take the derivative of the denominator and evaluate that new limit. And the important thing to remember here is that, we're starting with fraction and we're talking about derivatives. Usually when we're talking about derivatives with fraction, we're talking about the quotient rule. But that's not what this rule is saying. This rule is saying take the derivative of the numerator and take the derivative of the denominator. We're not taking the derivative of f over g. We're separately taking the derivative of f and g as part of this rule that we just proved. This is going to make a lot of the indeterminate limits that we did in the first unit that were kind of irritating quite a bit easier. So here we have the limit as x approaches 2 of x squared minus 4 over x minus 2. And if we plug in 2 to this, we can see that this is 0 over 0. And on the AP test, they'd like it if you indicate that you're using L'Hopital's rule. So we're going to say using L'Hopital's rule, the limit as x approaches 2 of x squared minus 4 over x minus 2 becomes the limit as x approaches 2 of the derivative of x squared minus 4 over the derivative of x minus 2. And you're not going to have to write this little step out. Normally, you'll just take the derivatives, 2x and 1, and now we'll just evaluate this at x equals 2. Well, that's just 2 times 2 over 1, which is 4. And that's the answer to this problem. And we can see that, the way we would have solved this a couple months ago is we would have factored x plus 2, x minus 2 in our numerator and canceled it with an x minus 2, giving us 2 plus 2, which is also equal to 4. So regardless of which method you choose to use, you're going to end up with the same answer. But now that we know how to take derivatives, a lot of the real complicated ones are going to become quite a bit easier. What's important, though, is to make sure that you actually check and see if it's indeterminate. Don't get so used to using L'Hopital's rule for indeterminate limit that you forget to check. Because if you have a limit that's not indeterminate and you try to use L'Hopital's rule, you're going to end up getting the wrong answer. So let's look at this one. First off, let's check and make sure it's 0 over 0. So if I plug in 0, we have the square root of 1, which is 1 minus 1 over 0. So clearly that's 0 over 0, which means we can use L'Hopital's rule. Now you're going to write out each time that you're using L'Hopital's rule, but I'm just going to say LH L'Hopital's rule. This tells us that this is equal to the limit as x approaches 0 of the derivative of the numerator, and the derivative of square root of 1 minus x is 1 over 2 root 1 minus x times the derivative of 1 minus x, which is negative 1. And then the derivative of the minus 1 right there is 0. And then all over 1. And now we'll just evaluate this and see what we get when x is 0. We got a negative 1 over 2 times the square root of 1 all over 1. Looks like that's negative 1/2 divided by 1. Or just negative 1/2. And that may be a little bit easier than trying to multiply that thing by the conjugate in order to solve that. Now here's one that we definitely took a long time to solve. We saw that it was 0 over 0, and we did that whole thing where we drew out a unit circle, and we put a couple of line segments through it and made some triangles and found some areas, and areas of the segment of the circle and areas of a triangle outside the circle. And we did a whole thing with the squeeze theorem. But now that we know that this is 0 over 0, and we know how to take some derivatives, this just becomes a limit as x approaches 0 of the derivative of sine, which is cosine x over 1, which is just the cosine of 0, which is 1. So that's going to make this problem quite a bit easier. We can see that it equals 1. It's still important to know, if you remember some of the problems similar to this, like when we did like the limit as x approaches 0 of sine to the 5th of 3x over 2x to the 5th, or something similar to that. That while this is 0 over 0, and I could use L'Hopital's rule, and in fact, you can use L'Hopital's rule multiple times in a row if the limit continues to be 0 over 0 or infinity over infinity. We have to do that a lot of times with this limit. We have to take a lot of derivatives. And the derivatives in that numerator are going to get excessively more complicated each time. So it's important to still know how to use that other rule, and where we can, the other rules where we can pull out the 1/2 and then pull the 5th power outside of everything and use the constants to solve it. So don't forget all the rules we used to use for our limits. Some of them are still going to be really important because L'Hopital's rule can sometimes be excessively irritating because of the derivatives. And additionally, there are a couple of cases you may come across a couple of problems along the way that are 0 over 0, where L'Hopital's rule actually fails to work out, and you have to find another way to solve it. Just be aware. And this was another one that we looked at when we were doing some of those trig limits. This is 1 minus the cosine of 0 over 0 plus 0 over 0. So we'll use L'Hopital's rule. Remember, you're going to write out that you're using L'Hopital's rule and make sure that you show that this limit is 0 over 0. And we'll then say the limit as x approaches 0 of the derivative of 1 is 0. And the derivative of cosine is negative sine. So we've got that negative in front of it. Negative sine will just be sine of x over 1, which gives us the sine of 0 or 0. And as we looked at previously, we found that this limit, using a little bit of manipulation of trig functions, was 0, but it goes a lot quicker this way. We'll do a few more here. This one, when we plug in 0, looks like we get the square root of 1 minus 0 over 0 squared, which is all just 0 over 0. So we'll go in and we'll use L'Hopital's rule, and we'll take our derivative. And this gives us a limit as x approaches 0. And the derivative of root 1 plus x is 1 over 2 root 1 plus x times the derivative of 1 plus x, which is just 1. So I'm going to ignore that. And then the minus 1 here becomes a 0. And the minus x over 2 becomes minus 1/2, all over 2x. And so now we'll just plug in 0. And it looks like what actually happens here is we get 1/2 minus 1/2 over 2 times 0, which is just 0 over 0. And so because this ends up being another indeterminate limit, well, L'Hopital's rule just says you can take the derivative of the top and the derivative of the bottom again. So before we do that, it might be helpful to rewrite that just a little bit. We're looking for a limit as x approaches 0 of, this is 1/2 of 1 plus x to the negative 1/2 minus 1/2 all over 2x, just so that it's in a form that makes it a little bit easier to take the derivative. And we'll say using L'Hopital's rule again, this becomes a limit as x approaches 0, and 1/2 of 1 plus x to the negative 1/2 will become negative 1/4 of 1 plus x to the negative 3/2. And then minus 1/2 there, that derivative is 0. And then the derivative of 2x is just 2. And looks like we end up with negative 1/4 times 1 to the negative 3/2, all divided by 2. And 1 to any power is just going to end up equaling 1. So we have negative 1/4 divided by 2, which is negative 1/8. And so if this had come out to be indeterminate, 0 over 0 again, we could just take another derivative of the numerator and derivative of the denominator. You can use L'Hopital's rule as many times as you need to until it ends up working out, as long as it continues to be either 0 over 0 or infinity over infinity. So let's take a quick look here at the limit as x approaches pi over 2 of secant x over 1 plus tangent x. And the first thing we'll need to think about is, well, what is this value here? And, well, the secant of pi over 2. If we think about it, secant is just 1 over cosine, and the cosine of pi over 2 is 0. So this is effectively looking like 1 over 0. Right? Secant is actually undefined at pi over 2. It approaches a vertical asymptote there. And as we're approaching pi over 2, that means we're getting very close to 0, which means we're actually dividing by a very small number, which means this is going towards infinity. And then in the denominator, the same thing's happening because we have 1 plus the tangent, which is sine over cosine. We know tangent, just like secant, is going to end up with an asymptote, a vertical asymptote at pi over 2. So this becomes 1 plus 1 over 0, which is also infinity. So we have infinity over infinity as our form here. And that means we can apply L'Hopital's rule. So we can look at a limit as x approaches pi over 2. And note that we're using L'Hopital's rule here. The derivative of secant, which is secant x tangent x, over 1 plus tangent x, which is just secant squared x. And it looks like we might as well cancel out those secants in the numerator and in the denominator before we deal with anything here. So this is just tangent x, right, limit as x approaches pi over 2 of tangent x over secant x. Now, if we plug in pi over 2 here, we already said that tangent's equal to infinity and secant's equal to infinity and pi over 2. We get infinity over infinity. So this seems like we want to use L'Hopital's rule again. And let's real quickly take a look at what happens if we do that. Well, using LH, L'Hopital's rule again, we end up with a limit as x approaches pi over 2 of secant squared x over secant x tangent x, which would just be a limit as x approaches pi over 2 of secant x over tangent x, which is infinity over infinity. Well, okay, we might as well use L'Hopital's rule again. So we'll say LH again. This then becomes a limit as x approaches pi over 2 of, well, the derivative of secant is secant x tangent x, and the derivative of tangent is secant squared x. And if we cancel out those secants, we end up with tangent x over secant x. And if we look, that's exactly the same limit that we had right here. And it seems like if we keep trying to do this, we're going to be in some sort of irritating endless loop where nothing worthwhile is ever going to happen. So instead of doing all of this, let's just make sure that as soon as we can simplify our trig fully, we do. So I'm going to just jump back over here and say, this is the same as the limit as x approaches pi over 2 of tangent x sine x over cosine x, all over secant x, which is 1 over cosine x. And in this case, we can eliminate those cosine x's in the denominator, and this becomes a limit as x approaches pi over 2 of just sine x, which would be the sine of pi over 2, and the sine of pi over 2 is just 1. So make sure that you're simplifying your trig functions rather than just kind of mindlessly using L'Hopital's rule for things that keep ending up being infinity over infinity. And this is the last one that we're going to look at here today. This is the limit as x approaches infinity of natural log x over 2 root x, which is infinity over infinity. Now, before, we didn't really have a good way to actually algebraically explicitly solve this limit. We just said, oh, the denominator is increasing more rapidly than the numerator, right? Because square root functions increase more quickly than log functions do over time as we go towards infinity. So we would have said this was 0, right? Because the denominator is getting bigger faster than the numerator. If it had been reversed, we would have said it's infinity because the numerator would have been getting bigger faster. But now that we know how to take some derivatives, we should actually be able to explicitly show with a little bit of algebraic work that this limit ends up being 0. So the derivative of natural log of x is just 1 over x. And the derivative of 2 root x is 2 times 1 over 2 root x. Those 2's will cancel. And we have a limit as x approaches infinity of 1 over x over 1 over root x, which it makes sense to simplify this. This becomes a limit as x approaches infinity of, well, if you have a fraction divided by a fraction, you just multiply by the reciprocal. So that root x goes up into the numerator. And in the denominator, we just have x. And here, it seems like root x over x can be simplified further. We know that root x is x to the 1/2, and x is just x to the first. So if we subtract the exponent, that's x to the negative 1/2, or just 1 over root x. So this is now a limit as x approaches infinity of 1 over root x. Well, the square root of infinity is infinity. This is 1 over infinity, which is approaching 0. So we can now algebraically solve some of those limits that previously we said we had to just kind of say, oh, well, one's increasing more rapidly than the other. But this is a better method to actually prove that that's what that limit is, to really prove that that denominator is increasing more rapidly than the numerator. And that's all we're going to talk about with L'Hopital's rule today. Just remember to make sure that the function is actually indeterminate, 0 over 0 or infinity over infinity, before you start using L'Hopital's rule. And be careful of getting into infinite loops with it.